by Hello everyone, I'd like to start now. And let me start by reminding you of two things. First, if you can squeeze in because people are going to try to find their seats. Thank you very much. The second thing is that we're going to have our first tutorial this Wednesday. And I'd like you to send me emails with your questions. And then if you ask me something by email, on Wednesday you're going to get an answer to your question. There are going to be some other questions which, as I suspect, we're going to have time to do. And we're going to see some of these questions later today in the form of quizzes. Instead of doing the quizzes here, we're going to do them during the tutorial. Now, before I continue from where we left last time, does anyone want to ask me any questions about what happened last week? I can hear lots of people have something to say, but they're not telling me. So if you have something to say, tell me, please. All right. Now let's go back then to what we were doing last time. And what is the last thing we've done last time? We discussed zero coupon bonds. What is a zero coupon bond? It's a bond which has no coupons. It has just one payment in the future, a payment of one of the face value. So it's going to be something that looks like this. Owner will receive, say, £1 in T years. And then we say this is a valuable piece of paper. People pay money for this piece of paper. We call this price for this piece of paper P. And this is another way of referring to the present value of £1 paid in T years. And then we said, wait a minute, we can think of this price in a different way. We can also look at T-year interest rates. So R, let's take R to be the T-year spot interest rate. I'm going to explain what I mean by spot later. Then we said there should be some relationship between P and R, the present value of £1 paid in T years, and the interest you get for T-year deposits. And then we figure out what this relationship should be. So we said, let's compare P to e to the minus RT. R is this R, and T is both these T's. And then we said, what happens if, what was the first case we've done? What happens if P is greater than that? We cooked a free lunch. What happens if P is less than that? We cooked another free lunch. We said the only relationship between these two numbers must then be an equality, and we got this statement over here. So we got the statement that says, this cannot happen. P cannot be greater than e to the minus RT. P cannot be less than e to the minus RT. So we are forced to conclude that P must be equal to e to the minus RT. And this is where we stopped, if I remember correctly. And now I want to take this a bit further. So what am I going to do next? I want to pretend that there is a zero coupon bond that matures in T years for any T. And I want to pretend that I can go to a bank and ask for what interest rates are going to apply for T-year deposits for any T. So I go to the bank and I say, I want to deposit money for pi over 3 years. And the bank says, sure, here's the interest rate. So how am I going to formally introduce that assumption? I'm going to introduce two functions. So the first one is a discount curve. A discount curve is a function of time, and it's a function that takes the time t to p of t. And what is P of t? That's, you can think of this in several ways. The first way to think about this is that this is the price of a zero coupon bond with face value of £1 and maturity in t years. And another way of thinking about this is the present value of £1 paid in t years. This is what this bond is doing for you. Okay? So P of t gives you a way of converting money in the future to its value now. So X pounds paid in t years has a present value of, so we take the nominal amount of the payment and we multiply this by P of this t. So P of t allows you to convert money in t years to money now. And we call this factor that you use here the discount factor, the t-year discount factor. So we have a function that for every t gives you the discount factor P of t. And P of t, I'm repeating myself here, is the price of a zero coupon bond with face value 1 maturing in t years. And I want to introduce another function of time, which is going to be the yield curve. So the yield curve is telling you what are the various interest rates for t-year deposits. So you go to the bank and you say, I want to deposit money for t years. The bank looks at y of t and it tells you that's your interest rate. So yt is the interest rate paid on t-year deposits. And here let me remind you that when we talk about interest rates in this course, unless I tell you otherwise, we're talking about continuously compounded interest. So we're going to assume that these functions exist, and I'm going to show you first a picture of them in real life, which is this picture I just managed to find here. So what is this saying? This is telling you about yields. It's a yield curve. And the horizontal axis here is time. And when you look at various values there, for example, if you look at y of 10 years, so there are various curves here. The latest one is this. So it corresponds to, so y of 10, it tells you precisely it's 1.59%. What is this 1.59%? This is telling you if you're lending money to the UK government, so that's a United Kingdom yield curve. If you're lending money to the UK government for 10 years, the interest you're getting is 1.59%. Okay? Notice that you have values from 1 week ago and 1 month ago, and there was a big jump. So if you're interested in these things, this is highly, highly interesting. But ignore my last sentence if you don't know what I'm talking about. So here's an example of a yield curve. And I'm showing you this yield curve for British pounds, or for loans to the British government. Different currencies with, and different governments and different corporations that issue bonds are going to have different yield curves. Okay, so again, a yield curve is a nice way of summarizing interest rates for all lengths of deposits. Where am I now? So the question now, the next question I want to ask and answer is, where is this picture coming from? Where is this graph coming from? How do the people in Investors Chronicle come up with this picture? And we're going to come up with our own pictures very soon. Okay, so this is what discount curves and yield curves are. And now, before I show you how to produce these pictures, these curves, let me summarize what happened last time by saying, before we had a relationship between P and R, the present value of £1 paid in t years and the t-year interest rates. So now we're going to write down the same relationship, but now it's going to hold for any t. And when we write it for any time t, what we're getting is P of t, P of this t, is e to the minus t-year interest rate, which is what we're calling y of t times time. So this now becomes, using the new notation, p of t is e to the minus y of t times t. Okay? Is this making sense? Remember, this means yes and this means no. Is this making sense? All right. So from now on, we're going to assume that you give me any time in the future, and I can tell you what is p of that t and what is y of that t. And now let me show you how you find out these functions. How do you compute p of t and y of t? And the first question should be, what data do you use to compute these functions? And the data, in practice, use many various different kinds of data which have to do with bonds, prices of bonds and interest rates. I'm going to show you a very simplified example of that. So in this example, we're going to look at prices of bonds. So we're looking at collections of bonds which have semi-annual coupons. So these are not zero coupon bonds. These are bonds that are going to pay you coupons every 6 months. Some of them are zero coupon bonds, but not all of them. And each row in this table is giving you information about one of these bonds. So there are 5 different bonds we're going to consider. So the first one, let's see, all the bonds in this example have a face value of £100. The first 3 have no coupons. They have 0 annual interest. And the first one matures in a quarter of a year. And then you go to the market and you observe this price from the market. That's the information we're going to use to construct this p of t and y of t. So you observe that this piece of paper that says owner will receive £100 in a quarter of a year, the price of that is £98.3. Okay? So we can go to the first row and we can translate this immediately into p's and y's, because what does it mean to say that the price of the first bond is 98.3? This is telling you that p of a quarter of a year is 98.3 divided by 100. Why is that? Because if you own the first bond in this list, what do you own? You own a piece of paper that entitles you to £100 in t years, and £100 in t years is worth 98.3. So how much do you pay now to get £1 in a quarter of a year? Well, you pay 1/100th of that. So p of a quarter of a year, which is the present value of £1 paid in a quarter of a year, is 98.3 divided by 100. Okay? Is this making sense? Okay. And now we can look at the second line here. And what is the price associated with the second line? That's the price of a payment of £100 paid in half a year. So how much do you pay now to get £1 in half a year? Well, you pay 96.5 divided by 100. And this tells you right away that p of 0.5 is this. And if you look at the next line, this is going to tell you, well, if you pay £93.7, you get the right to get £100 paid in a year, and nothing more, nothing less. And this is telling you that p of 1, what people pay for £1 paid in 1 year, is 93.7 divided by 100. So this is not too difficult. And now that I know the p of a quarter, a half, and 1, I can compute y of a quarter, a half, and 1 by using this formula over here. So if I know p of t, and I know t, I can solve for y of t by taking natural logarithms of both sides. Right? If I take the natural logarithm of both sides, what am I getting? I'm getting log of p of t is minus y of t times t. And if I want to know what is y of t, once I know what p of t is, I'm going to get that y of t is minus log p of t divided by t. And here's a question that you should be asked. Well, some people. Okay, here's a stumbling block that some people stumble over sometimes. I'm writing log here. Which log is this? It's the only interesting log in the world, which is the natural log. I took the log to get rid of this exponent e over here, this exponent over here. So I'm taking the natural log of both sides. So in this course and in life in general, whenever someone writes log, this means what in high school you call ln, natural log. Okay? So in this course, I say log, I mean natural log. Okay, this was straightforward. What happens next? So we can find, based on market data, we can find the values of the discount curve for t is equal to 1/4 and 1/2 and 1. Let's see if we can make some more progress. Let's try to figure out what is p of 1.5. So how do we find out what is p of 1.5? So let me copy the same table we had before. And let's ask ourselves, what do we know? What is the fourth line here? What is the fourth bond telling us here? So we look at this bond and what do we see? We see it matures in 1.5 years. And this is not a zero coupon bond. This bond does have coupons. Let's try to figure out what the coupons do for us. So there's going to be a special time, which is in 1.5 years, 1.5 years. What happens here? So here's my time axis. And here's now. What happens in 1.5 years? Two things are going to happen. I'm going to get the face value, £100, and I'm going to get the semi-annual payment, which is 4% of the face value. So every year I get 4% of 100, which is £4. I get paid this £4 in 2 payments, 2 installments. Each one of them is a payment of £2. So here I get 100 plus £2. Six months before that, when in 1 year, I'm going to get a coupon payment of £2. And 6 months before that, times 0.5, I'm going to get another coupon payment of £2. This is what this fourth bond does for you if you own one of these. Okay? So now you look at this and you say, people are paying, how much are they paying for this piece of paper? A piece of paper that promises these payments in the future. They're paying £95.5. So people say, here's £95.5. Here are these payments. So what do I know about this £95.5? This is the present value of this collection of payments. This is what I'm willing to pay now to get these payments in the future. So let's write down what are people willing to pay now to get these payments in the future. Well, it's £2 times P of 0.5, because this is what people pay now to get £2 in half a year, plus £2 times P of 1, because this is how much people are willing to pay for this payment in the future, plus 102 times P of 1.5. Right? Do you see where this is coming from? Is this making sense? Okay. And then we look at this and we say, we computed this, we computed that, we observed this in the market. The only thing we don't know here is this number over here. So let's solve for this number. Okay, so let me repeat myself. I look at the fourth bond. It tells me that this equation must happen. I know all the numbers here except for p of 1.5. I can solve for p of 1.5, and I get something. And this is p of 1.5. And then I can find what is y of 1.5. What is the 1.5 year interest rate by using something that used to be here, by using this. And I get the 1.5 interest rate. And now, can we find the 2-year discount factor or the 2-year interest rate? So we look at the last bond in this list and we say, what is this fifth bond in this list doing for us? If we have one of these, what happens to us? Well, we're going to get, in 2 years, we're going to get the face value of £100. In addition to that, we're going to get coupons, semi-annual coupons of, each one of them is going to be half of 6% of £100. So each coupon payment is going to be £3. And I'm going to get a coupon payment in 2 years, another one in 6 months before that, another one 6 months before that, another one 6 months before that. So we can write down the present value of all the payments generated by this fifth bond, and it's going to be the left-hand side of this equation. So this is what people should pay now to receive these 4 payments in the future. And you can set this equal to what you observe people are actually paying for. So you can set this to be equal to what people pay in order to receive these payments. So you go to the market for these bonds and you observe a price of 97.2, and you set this expression here to 97.2, and then you say, we know what this is, we know what that is, we know what this is. The only thing we don't know in this equation is p of 2. We can solve for p of 2. You get some number, which is very uninteresting, and then you can compute y of 2 using this formula over here, and you get the 2-year interest rate, which happens to be something like 7.42%. All right? This method of constructing discount curves and yield curves is called the bootstrap method. Here, the bootstrap method. Why the bootstrap method? That's because of a story of the Baron of Munchausen, who wanted to lift himself out of somewhere. So he held on to his bootstraps, and he pulled really hard up his bootstraps, and then he started floating in the air. Okay, don't try this at home, it's not going to work. But here you managed to get some lift out of nothing, and here you managed to get some data by just doing something which doesn't seem to be very substantial. Anyway, this is for some weird reason called the bootstrap method, and this is what the bootstrap method is. Do we have any questions about this example? Okay, so now, after this example, we should have a feeling of where these functions come from. Where does p of t and y of t come from? So there are people in various places looking at prices of lots of things and cooking them. The calculation for these things in general is going to be substantially more complicated than this simple example. You're going to have to do some clever stuff to resolve inconsistencies in your data. But after you do that, you cook all these numbers, and out come these yield curves and discount curves. Okay, so now let's talk a bit about risk. So I showed you a yield curve, and that yield curve referred to lending money to the UK government. Now, if you lend money to the UK government, you can be pretty sure you're going to get your money back. I don't think the UK ever defaulted on its debt. But suppose instead that you're lending money to, so let's see, what would be a good example now, to Italy. So I don't know if you follow the news, but there is a big mess in Italy. And so what happens if you lend money to Italy? So some people think, including myself, that maybe if you lend money to the Italian government, you're not going to get this money back. Okay? How does this get reflected in the prices of Italian government bonds? So if you suppose that you say, when I lend money to the UK government, I'm going to expect an interest rate of 1.5% or whatever it was that we observed before. When the government of Italy comes to you and says, oh, please, please lend us money, what are you going to say? You're going to say, if I lend you money, it's not clear that I'm going to get my money back. I want to compensate myself for this extra risk I'm running by lending you the money and not the UK government. So what am I going to demand? I'm going to demand higher interest rates. Now, why do I demand higher interest rates? Because bad things happen. So let me show you two examples of bad things. Here's the Iceland bank crisis in 2008, I think, or 2009. And you had all these universities full of clever people lending money to Icelandic banks, which then went bankrupt, and all this money was lost or almost lost. So that's one bad thing that happens when you lend money. There's the risk that you're not going to get it back. So this is the case of Icelandic banks. Cambridge faced losses of £11 million, which is 3% of its total market deposits, and so on. Or this can happen also to governments. So in 1998, the Russian government said, I borrowed lots of money from you, and I'm really sorry, but I ran out of money. So I'm not going to pay you back. All these coupons that I should be paying twice a year, I'm very sorry, but I ran out of money. So if you had these Russian government bonds, well, you were in trouble. All these investments were silently worthless. So there's risk involved in lending money, and prices of bonds and interest rates reflect this risk. So if you're looking at risky bonds, if someone sells you this piece of paper, but you're not quite sure that you're going to see this £1 in the future because that person may go bankrupt, then you're going to be willing to pay less for this bond. So risky bonds are cheaper, which then by looking at this, it will tell you that interest rates are higher when you lend to risky counterparties. Okay? And you can also see the effect of risk on prices of bonds and on interest rates when you compare secured loans to not secured loans. So what is a secured loan? You get a loan for buying a house. If you don't pay your loan, if you don't repay your loan, someone comes and takes your house. So the amount of money that the lender is going to lose is limited because they can always take your house, sell it, and get back their money. So when you take a loan to buy a house and your loan is secured by the house, you're going to pay a lower interest rate than when you go and take a loan to go on holiday. Okay, now let me show you a striking example of that. So these are 10-year interest rates that I observed in 2010. 2010 was in the midst of the euro crisis. And what's special about all the countries, all the governments listed there is that the currency for all these countries, what is the currency for all these countries? What currency do people in Germany use? The euro. And what currency people in Denmark use? The euro. These are all euro countries, right? So if all these counterparties, if all these governments were indistinguishable, if they were all the same, if they were all risk-free, when you lend money to Germany, you would be paying the same you would be getting the same interest rate as you would be getting from Greece, right? And the fact that we see these huge differences, so the factors of 5 or something like that. So when you lend money in 2010 to Germany, you would expect an interest rate of almost 2.5%. If Greece came to you and said, I want to borrow some money from you, then you said, I'm not going to charge you 2.5%, I'm going to charge you 11.5%. Why is that? That's because at the time, the Greek government did not seem very capable of repaying its debt. So you compensate for this extra risk you were running with Greece by demanding higher interest rates or by paying less money for their bonds. Okay? Okay. Now, this is about the last time I want to look at risk, counterparty risk. So from now on, when we talk about interest rates and bonds, we're going to disregard risk. And then we're going to assume that every currency we're going to be interested in has a discount curve and a yield curve, which refers to risk-free borrowing. So we're going to assume that all interest rates are interest rates which apply to counterparties which have no risk associated with them. And we're also going to assume that everyone can borrow and lend money at these rates, and that they can do that in unlimited quantities. Okay? That's not true if I try to borrow money from a bank, or if the UK government tries to borrow money from a bank, we're going to be paying very different interest rates. But for the purposes of our course, we're going to ignore risk. We're going to assume that all counterparties are risk-free. Okay, so I mentioned that we're going to have a tutorial on Wednesday. During that tutorial, we're going to be doing things like this. So instead of doing this now, just notice this question, which appears in your notes. On Wednesday, we're going to look at this example and we're going to solve it. And there are going to be 1 or 2 more such questions, which I'm going to show you today. Just, it's a good idea to have a go at them before Wednesday, and then Wednesday I'm going to reveal how to solve this problem. Okay, now, next I want to tell you about forward rates, but before I show you what forward rates are, let me ask you if you have any questions about what we've been doing so far. Any questions about the bootstrap method, riskiness of lending? Okay. So remember that at some point I talked about spot interest rates. Now in finance, spot means now. So when I talked about spot, the T-year spot interest rate, I was talking about you going to the bank and saying, I want to borrow money for T years between now and T years in the future. So now I want to discuss a slightly different situation. Now we're going to go to the bank and we're going to say, I'd like to borrow from you money starting from some point in the future until some point later. So how does that look like? So I want to borrow or deposit money in the future, which means that we are now at time 0, and there is going to be some time t1 in which I'm going to start doing something, and that something is going to last until some time t2. So in the example I'm giving you there, I want to deposit some money time t1, and I want to collect the balance at time t2. And the question is, when I do that, can I agree, or is there a sensible way to agree now at time 0 on an interest rate which is going to apply for this future period of time. So what is the interest rate here? Is not one of the interest rates we've been looking at so far. Why not? Because it's not something happening from now until some period in the future. It's something that is going to start at some point in the future and last for some period of time. So the question is, how do we find the interest rates that should apply for this period of time in the future? So in this particular example, I want to deposit £1 in T1 years and withdraw the balance in T2 years. I go to the bank and I wonder what should be the interest rate, which I'm going to call R12, for this deposit. So what is the interest rate I'm going to calculate for my deposit in this period of time? And these interest rates are what we're going to call forward rates. So these are interest rates that apply for periods of time that begin in the future. So let's try to figure out how to do that. So suppose that you give me this forward interest rate R12. So let me show you two things that you can do with your money. Let me show you actually three things you can do with your money. So the first thing is you can take £1 and you can deposit this for T1 years. If you deposit it for T1 years, let's take R1 to be Y of T1. So that's the T1 spot interest rate. So first, after T1 years, you're going to get your £1 times e to the R1 T1. At time T1, you're going to say, I'm going to deposit now my money at this pre-agreed interest rate that we agreed. We signed a contract at time 0, committing ourselves to this interest rate. So I'm going to take the balance of my deposit, which is this one, and I'm going to deposit my money for T2 minus T1 years. So from time T1 to time T2 at the interest rate we agreed at time 0. So that's one thing you can do with your £1. Another thing you can do with your £1 is to say, take your £1 and just deposit it for T2 years. Now let's take R2 to be Y of T2, the T2 spot interest rate. So when you do that, when you deposit your £1 from now until T2 years in the future, you're going to get back your £1 times e to the interest rate, which is R2 times T2. So these are two different things you can do with your £1, and it looks plausible that no matter what you do with your £1, these two outcomes should be the same. Otherwise, something is not right here. So that's one way of thinking about this number over here. And what I'm going to be doing very soon is to showing you what happens, what is not quite right if this equality doesn't happen. Here's another thing we can do with our money. So suppose that I want to arrange for me to deposit money at £1 in time T1 and to withdraw the balance of my deposit at time T2. How else can I do this? I can say, so I'm giving names to the T1 and T2 interest rates as I did here, R1 and R2. I could start by borrowing money for T1 years, this precise amount of money for T1 years, and deposit this amount for T2 years. So what happens when I do that? So after T1 years, I have to repay my loan. How much money do I have to repay at time T1? I started by borrowing this much for T1 years at an interest rate of R1. So I have to repay the amount of money times e to the R1 T1. And what is that equal to? How much money do I have to repay when I borrow this amount of money for T1 years at an interest rate of R1? it's important for me to know that you know this answer. So if you know this answer and you're being shy, then don't be shy. How much money are you going to have to repay at time t1? Okay, everyone, roll up your sleeves, take a piece of paper, work on this problem. You borrow e to the minus r1 t1 pounds for t1 years at an interest rate of r1. At time t1, how much money do you have to repay? Come on, I want to see you rolling up your sleeves, taking a sheet of paper, writing something or another, scratching your head, looking at your notes.
Excuse me, can you speak again the question?
Sorry?
Could you speak again the question?
Okay, the question is, you borrow some number of pounds. That number of pounds is e to the minus r1 t1 pounds. You borrow this amount of money for t1 years at an interest rate of r1. You wait for t1 years, someone knocks on your door, demands their money back. How much do they demand? Don't look at me. Look at your piece of paper. The answer is 3 letters. 1, right? The amount of money times e to the interest rate times time. E to the minus r1 t1 times e to the r1 t1, which happens to be 1. Okay, so you do that. At time t1, someone comes to you and says, I want £1. So you deposit £1. And then at time t2, let's see, we started with this amount of money. Now we're going to borrow this amount of money and we're going to deposit this amount of money for t2 years. So what happens at time t2? We deposited e to the minus r1 t1 pounds for t2 years at an interest rate of r2. So after t2 years, the balance of our deposit is this times e to the interest rate times time. Okay? So the effect of this strategy is at the time t1, we deposit £1. At time t2, we get this much. So this is telling you that this should be the same thing as your £1 times e to the interest rate that you agreed on, which is R12 times the period of time between your deposit of £1 and the withdrawal of your deposit. So that's another way of finding a plausible formula for R12. Right? Is this making sense? Can you give me some signs of life? Can you do something? Okay, so now let me, instead of suggesting what the answer should be, let me convince you that this is the answer. So I'm just repeating myself here. So from either way, this way or that way, you can write down what R12 is. So you solve for R12 by taking logs of both sides of various things, and then you can get this. And the statement I'm going to make now is that when you go to the bank and you agree on this interest rate that is going to apply for this future period of time, you must agree on this interest rate, R12, which is given by this expression over here. So this number over here is what we're going to call the forward rate for the period from T1 to T2. It's given by this formula. And now let's make a statement about this interest rate. So to make the statement, so I just gave you a formula for something. Where does this formula come from? It comes from my brain. But we're talking about finance here. Finance is about the real world. So I want to compare what happens inside my brain to what happens in the real world. And if my brain is functioning correctly, then these two things should be the same. Otherwise, I'm not teaching you anything very useful. So what is the thing I'm going to observe in the real world? It's going to be a contract, which is a forward rate agreement. What is a forward rate agreement? It's a piece of paper which has small print in it. When you read the small print, you read party A will either deposit or borrow some amount of money, let's say £1, from time t1 to t2 at an interest rate of R. So what is the thing that I observe in nature? It is this. So I observe what people are agreeing now, what the interest rates people are agreeing now for these future periods of time. So that's what you observe in the real world. What we observe in our brains now that we know is this hypothetical, theoretical number R12 and proposition 1.1. Congratulations, this is the first proposition in the course. Is these two numbers are the same. Okay, how do I convince you that these two numbers are the same? How long do I have to convince you? So, okay, I have 3 minutes. I'm not going to finish the argument, but I'm going to start it. How do I convince you that two numbers are the same? How did I convince you that two numbers are the same so far? So remember, I convinced you that if you observe P of t and y of t, I convince you that P of t is e to the minus y of t times t. How did I convince you that this is true? Can you say it again? Just say it again. I didn't hear you.